Let's assume we have two orthogonal axes, and they are perpendicular as well. And now we have a second orthogonal axis on top of that, but it is slightly rotated about the center, and this center rotation now leads to the fact that we have an angle of, for example, alpha at this location, and we will also have an angle alpha at this location and at this location and also here. And this is often quite helpful when we try to calculate the distance or the kinematics of a certain mechanism, which I will show you now. Let's assume we have a coordinate system with our axes x and y. Then we create a mechanism with one step and a second step, and then we have a translational joint moving along the y-axis and two rotational joints connecting the steps. What we try to calculate now is the position of this translational joint here in dependence of an angle alpha at this position here at the bottom, and then we have an additional angle beta. And now we want to know the distance depending on these two angles and these two distances. We will call these distances R1 and R2. And we move this now to the left to have a little bit more space to calculate the position. We begin by calculating to this point here. x1 equals, in the x direction, the cosinus of beta times L1, because we have this angle here, the cosinus is this direction, and for the y1 position we have the sine of b2 times 1. But now if the angle gets bigger, we don't go in the following direction here, we go in the minus direction, and therefore we need a minus sign in front of this equation. Now we calculate x2. x2 is the position of this translational joint. This position is equal x1, and now we want to get from here to here, and this is not so straightforward. And now we are going to use what we learned on the previous slide. We generate our first orthogonal coordinate system, and then we rotate one approximately around the center. And now we can explicitly state that this is the angle alpha, and I know that this is the angle alpha, and therefore I know that this is also the angle alpha, so I translate this information from here to this position, and therefore we have our angle alpha here as well. So in our x direction we multiply the distance of L2 times the cosinus of alpha, but we don't go in a positive direction if alpha is 0. Instead, we go in a negative one, and therefore we need to multiply this part with -1. What I'm going to do now instead is erase a plus and write a minus. Okay, so let's now calculate y2. y2 equals y1, so we are now at this position, and we need to subtract an additional L2 times sine of alpha, and there we got the position, and from my point of view it got a lot easier when we used this little helpful drawing to know where our angle alpha sits again. And this is how we found the counter angle, opposite angle.